said something
I know
else
I
like
didn't
you're gonna
sound
go to
the
hell.
mathematical lab.
And so now that's like our big joke.
It's coming shortly.
I was looking for it.
Yeah, I know you were. I'm sorry. Like I said this weekend. But I have internet in my house and I'm all set, so I'll get on that. And,
Wait, did they come on that Friday or did you get another free month?
No, they came on Friday.
Darn.
Oh.
I know it is sad. But oh well.
Damn them for doing their job.
It's alright. I dropped my cable anyway. I had everything, like every channel in the man. And I'm sure I will again, but for the time being, I'm being all stoic. I'm like, I just want internet service. And the Bright House operator's like, are you sure about that? I'm like, yes. So we're gonna try the Netflix thing. It's like $120 a month extra just for all that cable. So.
Well,
Netflix sucks though because nothing
cable.
you ever want to watch. If you name anything you want to watch, it won't be streamed instantly.
And kids in the hall as well.
They do.
So
well,
I
you can
agree.
just go to Hulu.
And that's probably why I'll go back to having cable, but I'm at least gonna try for a month.
I tried. I went without my TV. I left my TV downstairs when I moved back, and I was like, I'm not gonna watch TV. I was like, I'm gonna be productive. Last night I gave up. I was like, oh, I want my TV back.
You could also do a Hulu Plus membership.
Yeah, Hulu.
That gives you a lot of other stuff.
I took my TV back, and now I just watch
it's
TV
like
all the
only
time.
$7.99 a month for Hulu Plus or something, and you get like a ridiculous amount of TV and movies and stuff.
But if you get
I have
bored,
cable now for
TED.com.
We have Netflix and stuff.
Some of the coolest videos ever. You can ask Jessica. I introduced her to it. And now she wastes her time like me.
Probably not as much time as you do.
Probably not. But you learn stuff. It's educational.
Well, that is one redeeming quality.
Just like the related rates.
No, actually, well, not exactly. In related rates, you do have quantities described by derivatives, but this is more of a hierarchical shift of the things that we solve. So here's what I mean by that. When I say you solve an equation, right? Normally what you do is you get a number out of it, right? Or you get a couple of numbers or something like that. What does it mean for that number to be a solution to that equation? It means that if you take the number and
Put it in.
put it back in, it should work, right? Okay. So it's the same thing. The difference though is that these equations contain derivatives, and these equations are actually much more useful because these equations actually describe a lot of the physical phenomena that we observe going on around us. Let me give you a very basic example of differential equation. Is that camera rolling?
Yeah.
Okay. Well, last summer I had an unruly bunch in my calc2 class. And I made an example here about someone being thrown off the building for them to understand the actual dynamics of how this plays out. So it doesn't matter if it's the mafia throwing somebody off the building or it's an object. But the point is, how many of you have had physics? High school? Okay, good. You all get this. All right. So imagine this. You've got a person standing up here, takes an object and throws this object, say downward, right? Imparts some momentum into it, some initial velocity, right? And momentum, of course, is mass times velocity. He's imparting some velocity here, and let's say that this is a height h. Like that. And the question is, what time does that object strike the ground? You do need to know a little bit of physics to make this work. It's specifically, you need to know Newton's second law. But that's all you need to know. With Newton's second law, you can actually solve this problem just knowing Newton's law, obviously, and the initial velocity and the height. So what is Newton's second law?
Force equals mass times acceleration.
Yeah, force equals mass times acceleration. Now, let's be a little more specific. It's actually the net force, right? So in a way, Christian, it's like the sum of the ambient forces acting on the object. That's what we consider to be mass times acceleration.
Although his was written in momentum.
You're right. You're well he actually did was he defined the force to be the time rate of change of the momentum, right? So in a sense, he's writing this in terms of the time derivative of momentum. And it's actually a good point to bring up. I don't know if any of you will ever encounter this, but with these little hats, don't worry about those. Those are vectors. I just busted out in the physics notation, but I think you guys get it. So how is momentum defined? Momentum P is equal to
Mass
Mass
times
times
velocity.
velocity.
good, mass times velocity, right? So if you were to actually look in the Principia, which is the book where Newton kind of laid all this out in the mid-1600s, this is actually how he defines force instead of mass times acceleration. He calls it the time derivative of the momentum. Well, if you actually work out this derivative, you end up getting something like this. But for the majority of situations we consider, especially in textbook kind of, academic settings, elementary physics approaches, we assume that the mass isn't changing with respect to time. Now you could see without, going too far off the deep end with esoteric examples, you take our shuttle launches, for example, they're staged. I don't mean fake staged. I mean, they happen in stages, right? Like at a certain stage, it'll eject a solid rocket booster. And so you see that in that system, in order for it to be continuous, which you want it to be continuous, you don't want some discontinuity in the piecewise function as this evolves in time. As it ejects those pieces, its mass is going to change, so you have to take it into account. But if you look at the simple cases where the mass doesn't change, what you're left with is this, and of course we know the derivative of velocity is acceleration, right? And that's where we get the F equals domain from. Good. All right. So I'm going to look at this, and there's no need to look at this in terms of vectors because it's not a two-dimensional projectile I'm looking at here. I'm just looking at it moving in the vertical direction. And if you guys don't mind, what I'm actually going to do is take down to be the positive direction. It seems awkward at first, but this thing has a finite trajectory, right? It's going to end here. So instead of taking everything to be negative because it's going down, we'll just look at that as a positive direction relative to being on the ball as being thrown down. All right, so in that case, well, let me ask you this. In addition to that, the one thing I left out of this, what is the primary agitator as far as accelerating this thing downward?
Gravity.
Gravity, right, the acceleration due to gravity. Which of course is m times g. Okay, so maybe I fibbed. So there are two things you need to know from physics. Newton's second law and force due to gravity, right? Now when you put this into the model, that is to say when you use Newton's second law, what you end up getting is that if we look at the net forces here, and we only consider the force due to gravity, we end up with an equation like this. Now, what I can do, and what I will do for you actually before the evening is out, is I'll come back and look at this again, except I will put in air resistance and show you how that works, right? So, for the time being, let's look at this in kind of an idealized state in which this thing is in a vacuum, right? So no air resistance whatsoever. Well, if you look at this equation, it looks algebraic in nature, but the truth is buried within the acceleration is actually a second time derivative. You guys remember it goes position, take a derivative, you go to velocity, take a derivative, you go to acceleration. So in terms of the position, and the reason I'm concerned about the position is because the nature of the question is what time does the object hit the ground. I'm going to need to know what the position is as a function of time in order to answer that question. So I'm going to look at this as the second derivative of the position is equal to g. Now going to Luciano's point, g does vary depending on where you are geographically, altitude-wise, but I'm going to assume that is constant here, right? And you'll see it makes a difference in the mathematics because when you start solving this, you're going to integrate, which I'll get to in a second. But if it's a function of time, you have to know how that gravity depends on time, and it becomes more complicated. So what you're looking at right here, guys, this is what's called a differential equation. And why do I call it that? Well, it's an equation which has derivatives in it. So the solution to this equation, you see normally, again, we think of solutions as being scalar quantities, numbers, constants, intervals, things like that. The solution to this equation is actually going to be a function. So instead of solving for some unknown scalar quantity, what we're doing is we're solving for some unknown function y that satisfies this condition.